So I'm still audible, right? Speak up and let
Yes.
me. Okay, great. And so, all right, so since you have so much hesitance in speaking up, let me just start by asking another thing, which is, so how do you feel about the connection between derivatives and integrals now?
Good.
Were you all here in the last session? Have you all seen the recordings? Okay, they're quite opposite to one another. Still don't understand the concept yet. Okay, that's fair enough. Yeah, right. Okay, so how much, okay, so I'm assuming that most of you are A levels or late high school students, how much more calculus have you seen? Have you ever seen a differential equation?
Yeah.
Okay, could you give me an example of a differential equation that you might have seen?
dy over dx equals 2x.
Okay, so it's a very fairly simple differential equation, dy over dx equals 2x. Um, and so for those of you who said that we have seen a differential equation before, what is in essence a differential equation? Yes, that's nice.
I think it's an equation, or it's an expression relating different differentials of or differentials of two variables, maybe, as my guess. But like, so the differential equations we've done probably in mechanics are those like linking velocity with displacement and time, and
Mhm.
that's basically what we've done in like in mechanics, right?
Right, so in mechanics, you might have seen equations like velocity displacement, where you, well, it's a simple relationship, right? Velocity, the derivative of a distance is what gives you velocity, and then perhaps you might have seen an equation perhaps for the velocity of some object or the acceleration of some object, and perhaps you differentiate that or you integrate that to get different other components, right? So if you take the expression for a velocity and then you differentiate it, then you get the expression for the acceleration of a body, right? But yeah, in its simplest form, a differential equation is again just another equation, except this time now instead of just involving the variables and the terms, additions, multiplications, etc., now they also involve derivatives of some variable with respect to another. And so what we have right now in front of us is perhaps the, well, I can imagine an even simpler equation than this, which is the derivative of one variable with respect to another is, let's suppose, a constant too, right? And that's the simplest possible differential equation that I can at least think of. Um, right, let me just get the people in the waiting. Okay, and so what do we do with a differential equation? So I'm sure you've solved questions related to differential equations. Um, how do you view this equation? How much information can you extract out of it? It's a simple mathematical statement, which says something like this. The, well, the rate of change, sort of, or well, let's not say the rate of change, let's say the derivative of y with respect to x is 2. And what else can you extract from it?
Y equals 2x
Y
plus
equals 2x. And how do you, so what you did right there is you integrated that equation, right? So you said dy over dx equals 2. You saw that there was a derivative with respect to x. So you
oh,
see,
I forgot to add and a constant.
and a
Any
constant. Okay, so what we do on this equation is we integrate both sides. Or in other words, you could use the fundamental theorem of calculus, which says that if you have the derivative of y with respect to x, you can just integrate and basically say I'm integrating both sides with respect to x. Over here, you use the fundamental theorem of calculus, which is y is equals to, and over here you have an integral, which is just a constant, 2x. And now you add a constant, 2x plus c. And this is the simplest possible differential equation you can solve. And what it has given you now is that an expression for y in terms of x. That is, the relationship between y and x is simple. Whatever y is, whatever x is, y is 2 times that plus some constant. So if I were to sketch this as a graph, what would it look like?
A line from the origin with gradient 2.
Okay, so
Sir, it would be
Yeah.
aligned with the gradient of 2 and would pass through y equals to c in the y-axis.
Okay, so someone said it passes through the origin, so that would be y equals 2x. Someone said it will pass through some arbitrary point with the same gradient, but this point is point C. And so the idea is that, of course, so far from the information that we have, either of these, there's nothing to differentiate either of these. Both of these are correct in a sense, because if you look at the original equation simply tells you that the derivative is 2, that it's a constant derivative. And if we look at these sketches, which of these lines satisfy that condition? Which one of them has a constant slope of 2?
Both of them.
Both of
So
them
don't
have a
both of
constant.
them have it?
Yeah, they do. Both of them have a constant slope. So if you were to ask me, what's the solution of dy by dx, I would tell you dy by dx by 2, I would tell you that the solution is actually not one particular relationship. It's an infinitely large family of, what I say, it's a family of solutions. Family of solutions or family of lines or family of curves, which is a solution to this equation, right? And there's nothing for me to differentiate between this solution to x or to x plus, let's say, to x plus 1 or to x minus 1, and so on. All of these are the solutions to the differential equation. Okay? Does that make sense? And all of them have the same property, that they have a constant derivative, they have a constant slope. It doesn't matter what exact position they have, as long as it satisfies the condition of it having a constant slope. Okay. And similarly, if we had a slightly more involved equation, let's add in just one more level of complexity, dy by dx equals to x. That is, the rate of change of y with respect to x is not a constant, it changes with respect to x as well. So before we even try to solve this equation, if I were to ask you to just think of it like this, that if I were to put a y here and put an x here, what can you tell me about the difference in the point, let's say over here, and the point over here, and the point over here? What's the difference? What information can you glean from this equation about these 3 points? On the y-axis, I have y, not dy by dx. This is y. Is there anything that I can say about these points from this equation?
Sir, it can't be a curve, right? Y can't be a curve, or can it?
Well, I don't know what it's going to be. I don't have the solution yet. There's nothing that I can say about the solution. Perhaps as far as specific points are concerned, what can I say about, at least in this space? Can I say when the value of x is 5, the value of y is 10? Can I say that?
No, because it's
We
going
don't
to
know
be
that.
x squared.
Yeah, we don't know that in particular, at least yet. But what I can say, at least by looking at this expression, I can say that when the value of x becomes large, then the slope, wherever that point may be, whatever that curve may be, the slope would be sort of large. If I say x is 5, then the slope would be 2 times x, which is 10, right? So at this point 5, whatever curve I have or line I have, it will have a slope of 10. So maybe if I denote this as a slope of 10, then maybe that's what I have. But I don't know whether it will be over here or whether it will be over here or here or here. We don't really know that, right? But what happens to this slope if I move a little bit over here? If I come over here and I ask, okay, what would be the slope at x equals 1, let's say?
2.
The slope would be 2. In comparison to these lines, now the slope would look a bit flat. It would look something like this. Now again, I don't know where the curve is, but it looks something like this, right? At that particular point. And I can see that there's a relationship that's going on, that whenever I go in this direction, the slope increases. Maybe later on it becomes like this, then it becomes like this, and then it becomes like this, and this, and this, and so on. The slope becomes larger as I move away from the, as I move into positive x-axis, right? And again, we don't know exactly where that curve is going to be because we don't have the solution, but I know I can say something about the tangents, or rather the slopes, okay? This is at least what we can expect. And in this direction, if you go, what would you see? If I go at -1, what kind of slope would I have?
A downward slope, like negative slopes.
A negative slope. So something like this. But exactly equals to -2. And again, as I go away from the y-axis, or rather I go in the negative x direction, what's going to happen is that the slope would look something like this, right? It will start increasing. The downward slope would sort of start increasing like this. And so this is sort of the information. Now, of course, there are infinitely many points. I have drawn these lines to be long, but these are really denoting what specifically the slope would be at that particular point. In particular, if I draw a line around -1, that particular slope is only valid for the line -1. If you move away even a little bit from -1 in the left or the right direction, if you go here, the slope would increase. If you go here, the slope would decrease and it will become flatter. And of course, exactly at 0, the slope, if you plug it in, the slope is kind of 0. So whatever curve it is, it's going to be flat about the line of y-axis. Does this make sense?
Yes.
This is what I've drawn. Something drawn here is something called the direction field that we can sort of glean just from the equation. And now, I believe that you might know how to solve this equation. Let's actually try to solve this equation. What is dy by dx equals to 2x? How do we solve this equation? Anyone?
So you could increase the power of the variable by 1 and then
Okay.
divide it by the new power, which is going to be 2x squared over 2, which is x squared only, plus c.
Okay, so what you're saying is I integrate?
Yeah, integrate both sides by taking the integral operator of dx on the other side, and then solve it
I
like that.
integrate with respect to x, and on the left-hand side, I'm left with y, because this was a derivative of y, which I'm integrating with respect to x, so I just get y. And on the right-hand side, I have 2x, which I have to integrate. So I get 2x squared over 2. The 2's cancel out, so life becomes slightly easy. But again, I have this constant of integration. Is this clear to everyone, how I solve that equation?
Yeah.
Okay, so if I were to sketch this just like I sketched this solution, this family of curves, what would this family of curves look like?
It would be a parabolas that across the y-axis at c.
Right, so it's simply a parabola x squared. You've seen quadratic equations. They look something like this. If I were to assume that c equals 0, then it would cross it at the origin. But of course, c doesn't need to be 0. C can be 1. If it were 1, then it will pass. It would be exactly the same curve, except it would be shifted above. If c were 2, then it's the same thing, except sort of like this. And if c were negative, then we get the exact same curve, except it passes the y-axis at a different location. So these are the different, again, this is a new family of curves, which are all possible solutions to my differential equation. X squared dy by dx equals 2x has these solutions. And now compare this solution that we've just drawn with the idea of the slopes that we had before, this direction field. And you can see that these family of curves are actually the realization of these slope fields that we've drawn, this direction field that we've drawn. If I were to sort of start off at this point and sort of follow these lines, because over here it's flat. So if this point were to move here, and then the slope would increase, then this point would be forced to increase. But then this point would be forced to increase even more as it moves rightward. And so it sort of follows this trajectory and becomes the right-hand side of one of these parabolas that we see here. And similarly, if I were to take this point and follow the slope line, then it increases, and then it increases, it increases again, and it's just following I'm just trying to ensure that at every point, the slope of the curve matches the slope that was given to us by this differential equation. And that's really exactly, you can see if you check it out, then the slope at this point is 0, and the slope at this point is positive, and the slope at this point is negative. Okay, so it does seem like we've actually correctly solved the differential equation. So that's just a simple differential equation. And so now you can have all sorts of complexities added to different, differential equations. So how would you make these equations more complex? Can you give me more examples of differential equations?
dy over dx equals y.
Okay, what else?
dy over dx equals to 4x squared plus x.
2x squared plus x. What else?
Sir,
Let's
dy
have at least 10 examples. dy by dx,
is equals to 7 upon x squared.
sorry,
7 upon x.
7 over x. Okay, more.
dy dx equals to sine x.
Sure, more. Make it more complex, as complex as you can make it.
So d square y. Okay, can go ahead.
Yeah,
And over dx squared equals to cosine x plus x.
all right, make it even more complex. Come on. Let's see how complex you could make this.
Sir, dy upon dx is equals to sine x minus 60.
Sine x,
Sine and then x minus 60.
x minus 60.
Yes, sir.
Okay, still not very complex. Even this, not very difficult to solve, I believe.
I
Even
think
this,
d square
most of
y
these,
over
dy dx
equal, either
dy
one of you. Mhm.
equals to e to the minus x squared.
There we go. Come on, now we're getting somewhere. What else?
d square y over dx square is equals to dy 3 dy by dx plus y
3 dy by dx
plus y
plus y. Okay,
plus 1 maybe. Just put it in.
plus y
No,
plus
plus
1.
y
Okay,
plus 1, yeah.
okay, more.
Sir, dy by dx equals to, let's take xy squared plus ln bracket 1 upon ex squared.
ln 1 over ex squared.
Yes, sir.
Okay, more.
dy dx equals to y over sine y.
Y over sine y. Okay, more. We have 10. Even then, we haven't really gotten very complex yet, I believe. Let's have 5 more. Let's see how harder this you can make this for me.
dy dx equals gamma x.
Oh my. Okay. So by gamma x, I believe you mean the gamma function?
Yeah.
Okay. Anyone else? Can you make this more difficult for me? You barely scratched the surface, by the way. There's lots to do here.
Maybe dy over dx is equal to I over cos x.
I over cos x. Okay.
Yeah.
So now we have some complex coefficients as well. That's fine. What else?
So let's take dy by dx equals to e to the power of sine x minus 60, and then that would be divided by I times cosine of x.
This one? Okay.
Yes.
More. Two more.
I think going into the inverses of trigonometric functions like tan inverse of I dy by dx equals tan inverse of x, maybe.
Okay. So we have the arctan function, tan inverse of x. Okay. What else?
Would it be like dy over dx equals to sec upon cot? Or does
Secant
that
function divided by cosine function?
COT?
Okay, cotangent function. All right. That's it?
Yeah, that's it.
Okay. So let me now give you a few classifications of how we, consider different differential equations. And there's actually, there are a couple of different examples here that fall into different classifications. So let me give you how we actually, we've actually just barely scratched the surface of how many different kind of differential equations there can be. For starters, the first thing that we notice is the order of the differential equation. And by order, we mean what's the highest order derivative that you have in your differential equation. For example, the first differential equation is first order because you just have a single, so the highest degree of derivative that you have is just the first derivative. There's only first derivative of y here, and this y is just as it is. Sorry, there's somebody else in the waiting room. Okay, right. So according to that, what's the order of all of these equations that we've written down? So this one is, what's the order? This one is first order. What about this one?
First,
Still first, this one.
first, second,
This is the first example where we start seeing a different, classification. This is a second order equation. And do you see any other second order? So there's
the eighth,
the eighth one, right? The rest are still first order. So all of these differential equations that you gave, as far as the first classification is concerned, they're sort of similar, except the only thing that you changed was the right-hand side function. Okay. So that's the first classification that we have. The other classification that we have is actually much more important, which is, well, let's not say important, but it's an important classification, which is whether it's a linear equation or not. And by linear, we mean that, so let me tell you what a linear combination is first, right? What's a linear combination? For example, if I'm looking at dy by dx and y, and let's say even d squared y by dx, then a linear combination of these would simply be multiplying each of them by a constant and then adding them up. For example, I could say alpha dy by dx plus beta y plus gamma d square y by dx. This is a linear combination that the terms are all being added. They're just being multiplied by a constant, and between them there's no multiplication. So now if I give you an example of a non-linear combination, then that could be something like this: y times dy by dx. This is not a linear combination. The reason it's not a linear combination is that dy by dx is being multiplied by the variable, by the other variable. Does this make sense?
Yeah.
Right. Everyone else on board? We're gonna ignore that. Okay, so everyone on board with what a linear combination is? So as another example, this is a non-linear case. If I had even, let's say, y squared, that also makes it non-linear because y squared is essentially y times y. If I had something like dy by dx whole squared, even that's non-linear. If I had any of these three multiplying by each other, that's non-linear. As an example, if I ask you what is y plus d squared y by dx, so let's say 5 times this, is this a linear combination or a non-linear combination?
Linear.
It's still linear. Well, you don't have dy by dx, but that's fine. And so if now we look at these different cases, and the only thing that we're going to check is the dependent variable, which is either y dy by dx, y and its derivative. We want it to be linear with respect to y and its derivative, right? So whenever you want to check whether a differential equation is linear or not, you just want to check whether these three, or if you have higher derivatives, perhaps you can have those higher derivatives being linear as well. But you only check with respect to y. You don't worry about the variable x, okay? So is this a linear equation?
Yes.
Okay. And so how can you say that? Because I was looking for something like alpha dy by dx plus beta y, and we don't have the second derivative, so we don't worry about that. So how does this equation fit
Beta
this
is
problem?
-1 and alpha is 1.
Right. So if we take this y on the left hand side, it just becomes dy by dx minus y. So the coefficient of y is -1, the coefficient of dy by dx is 1, and they're just being added together, right? Subtraction, addition, same thing, no difference. Okay. So this is linear. And so let's see how many of these are linear. Everyone on board with this definition? Firas, Fatma?
Can you please just go over it again?
Sure.
Yes, sir.
So for it to be linear, you're just looking at how do these terms interact, y and its derivative. They shouldn't be multiplying with each other. They shouldn't be squares or anything. If they are interacting in any way, they should interact in the following way. For example, if there's a dy by dx, the only thing that can multiply it is either some constant like 5, or even perhaps even something that is in terms of x. That's also fine. But there should be nothing that's in terms of y that's being multiplied with it. So I can't have something like this. And if there is a term in y, then it should be added to it. And you can have some multiplication of y with something else, for example, a 5 or a 6 or an x even, that's fine. But nothing So y and its derivatives should be in a linear combination with each other, right? So linear combination is something that you have these three things and they have some constant being multiplied with them, either constant or some function of x, and the rest of the things should just be addition. There should be no multiplication between them. Does that make sense?
Could the explanation of a linear function also be that whichever variable the equation is in respect to, the power is in more than one?
So we can't have that because even for a second order differential equation, you can have a linear second order differential equation. For example, this one. This is a second order differential equation, but it's still linear because it's d
Oh,
squared
so
y over d.
it just shouldn't multiply with like other variables that are going to make it an increased power, something like that.
Something like that. So something like if I were to multiply it with a y, that's a non-linearity there.
Okay, I get it.
But if I were to
Thank you.
add a y, that's fine. If I were to square it, that's also a problem because by squaring, you're actually doing what? You're multiplying it with another d squared y over dx squared. So that would involve another non-linearity. Okay. Does it make sense?
Yes, sir.
Okay. So let's try to classify them. Let's see if we have any non-linear equations here. Is this a linear equation? As
Yes.
far as y and it's so linear, I mean y and its derivative should be in a linear combination. In a linear combination. Okay, so is this linear? The second one.
Yes, sir.
Yeah, dy by dx is fine. It's the coefficient here is 1. That's fine. There's no other term in y or a derivative in y. So that's fine. What about this one?
Yes, it's linear.
Number 4.
Yeah.
Scan this list and tell me if you see any non-linear equation.
10.
10. That's the first example of a non-linear equation. Y over sine y. Y is interacting with itself. So that's the first example that we have of non-linear. Any other example?
Nine.
9. There's a term in y squared here. Squaring is also not allowed because if you square it, just means you're multiplying it with another y, right? So that also makes it non-linear. So this is also a non-linear equation. This is a non-linear equation. Any other equation look non-linear?
12.
12. Why do you think 12 is non-linear?
No, sir. I'm sorry. I just misread, or I guess why I said. I just thought that, like, at one instant, I thought that because IR is being divided by cosine of x, then that would be a case. Then I just remembered it should be a y term in order to be a non-linear.
The non-linearity should be for y because you're classifying the differential equation which is in terms of y, right? So this is a completely fine. It's a linear equation as far as classifying this as a differential equation. But of course, this term is a complicated term. There's a complex number involved and it's dividing by cosine x. That's fine. You don't have to worry about that. I can give you a general form, but I don't want to give you that right now. I just want you to remember how to just check simply. So the rest, I do believe they're all linear. This is linear. This is the second derivative in y, not being multiplied by anything else in terms of y, so that's fine. This is the first derivative, no other term in y, first derivative, no other term in y. What about this one? Number 8.
Linear.
It's linear because if I were to move this term and this term on the left hand side, this actually is a perfect example of a linear combination. You have d squared y over dx squared. You have plus 3 times dy over dx, and you have plus y. They are all different terms. Nothing is being squared. The coefficients being multiplied are also not in terms of y. So it's a perfectly fine linear equation. And on the right hand side, you have a 1. So this is also linear. And you can check that you have linear. This is linear. Only 2 examples are number 9 and number 10, which is why I was saying we've barely scratched the surface. You could make a very, complicated equation that looks like this. You can have and perhaps even I can increase both of these complexities. I could make it a higher order equation and I could make it a non-linear equation. For example, y cubed times d 4y dx fourth plus y squared dy by dx plus, let's say, y cubed equals to sine x. Now, the order of this equation is 4, and it's also a non-linear equation because there is this interaction. There's a cube on y, there's a square on y, there's this interaction, and so on. Even this term is a non-linear term, y cubed. Okay. So you can make a differential equation more complex by increasing the order, or by adding in some non-linearity, and so on. Okay. So it seems what's important are the terms in y and the derivatives of y. So let me combine these. Let me say this is some function of y and its derivative. So I say it's a function, this whole expression is a function of y and dy by dx and d squared y by dx squared. If I wanted to make my life slightly easier, I would go to Newton's notation, which is y, y prime, y double prime, y triple prime, and so on. And these are the terms that I can have on the left-hand side. And on the right-hand side, I could have a function of x, some small function of x. So now this can be sine x, it can be cosine x, it could be anything. And you could also have it in terms of, y as well. You could have an involvement of y there, which is like y sine x, or so on and so forth, right? So maybe I remove the y from here, keep the derivatives on the left-hand side, and this is the right-hand side, okay? Is this clear? So I'm just now giving you a general form of a differential equation, okay? And you can have an involvement of the x variable here as well. For example, if I were to put an x here, that's fine. That's a differential equation. It's terribly difficult to solve, but there it is. It's still a statement about the derivatives of y, and you have to solve it. Does this make sense?
Yeah.
Any questions so far?
No, sir.
Okay. So we've just looked at a few examples, and these are all, by the way, these are ordinary differential equations, what we've just seen right now. by ordinary differential equations, we mean that there is only one dependent variable. The dependent variable here is y. Okay? If you have multiple dependent variables that depend on x, then what you get is a partial differential equation. Okay, partial differential equations could look something like this. It could be a derivative, and I don't know if you've seen partial derivatives yet, but I'm just going to put in a partial derivative here and just leave it at that. That the partial derivative of y with respect to x, of let's say with respect to, so let's say y with respect to z plus partial of x with respect to z equals 0. So this is just in other words saying, or rather, let's make this z and let's make this x. So now what we're saying is that there are two variables, the second derivative of y with respect to x and the second derivative of z with respect to x, they add up to give you 0. This is a partial differential equation. Another differential equation could be something like this. It could be that the rate of change of, let's say, some quantity u with respect to time could be related to, how do we say? So we could have it as, so let's make this the first derivative and let's make it the second derivative with respect to x. You could have something like this as well. Okay. Does this make sense? So these are partial differentials. But of course, if you haven't seen this partial differential, this partial derivative yet, this might be new to you. So let's not worry about this. There's already enough complexity in ordinary differential equations. And you can see that things are not as simple. There are, even for a simple equation, there is a family of solutions. And so you can imagine that solving these differential equations. Now let's see if we try to solve this equation. Is this an easy equation to solve?
Yes.
How do we solve it? I have dy by dx equals to y. How do I solve it?
It has two solutions, y equals e to the x and y equals 0.
Y equals 0. So this one is a trivial solution, right? If I were to plug in y equals 0, then that's really not an interesting solution. If I plug in y equals to 0 in this one, would it satisfy this equation?
Not for all x.
Not for all x, right? So in this particular example, you have two functions. It could either be a constant function, which is 0, and that's usually not the interesting example. What's the interesting example to solve is what we call this as the trivial solution and this as the non-trivial solution, that it has some information in it, that it's not just a 0 constant line that doesn't have any particular information. So let's not talk about these equations, at least for now. Let's talk about why they're important. And they're important because they help us to model phenomena, right? Differential equations are highly, highly useful. Any dynamical system that you can think of, any physical system that you can think of is almost always modeled by a differential equation, right? If you make a statement about that the rate of change of something is proportional to something, if you say, if it involves orbital, like if you want to describe the motion of a pendulum, then you describe it in terms of what the force on the pendulum is and how it's moving. Or so let me write down a few examples. In population models, you usually see differential equations of some kind, and I'll give you an example of this just now in a bit. If you have some physics phenomena, let's say you want to describe the motion of a pendulum, if you want to describe the motion of a spring system, or if a spring pulley system, Or if you want to describe the motion of planets orbiting around each other, or in a solar system, let's say you have a binary star sort of a system where two planets are sort of orbiting each other, or you have a solar system where you have a sun in the middle and you have planets around them, and all sorts of applications. Let's suppose you wanted to describe if you had a single, let's say, let's make it, if you had a spoon, right, and you started heating the spoon from one end, then the distribution of the heat along the spoon is modeled by the heat equation. Again, another differential equation that we have, which tells us how would the heat dissipate through this material, right? Suppose you had a bucket, sort of a pond, let's say a pond or a bucket where you have some fluid, and if you were to drop something in the middle, what kind of wave would you generate and how would it travel across? That's modeled by a wave equation. And all of these are differential equations of some kind, right? And generally, differential equations are not easy to solve. You will study, when you go to a calculus course, you will study lots of ways of solving differential equations, but most of them would be limited to first or second order, and most of them would be linear. Unless there are specific cases, there are specific, symmetries or something for you to exploit, nonlinear and higher order equations are very difficult to at least solve analytically. Okay? But there's lots and lots of physical phenomena that you can model with a differential equation. Even, for example, right now, the laptop that I'm using has some battery that's being used. Now, the charge dissipation in the battery, or even the heat dissipation, all of them are modeled by some kind of differential equation. Okay. So here's an example, a very simple example. We have a couple of diagrams here, and I just wanted to show the diagrams first before we look at the equations, because the diagrams are actually, the graphs are easy to understand. What we have here is an example of what you see in a predator-prey population. So suppose you have a predator like a lion or a fox or anything that hunts another prey, and the prey could be a deer or a rabbit, right? And what we see here is the trajectory of their expected population, the expected trajectory of their population. And there are two diagrams that I want to look at one by one. If you look at the diagram on the right-hand side, notice something, that there is a cyclical behavior. So on the x-axis, you have the time in years, and on the y-axis, you have the respective population. So look at this graph for a few minutes, and then tell me what you see happening in this graph and whether it makes sense or not.
It makes sense.
What is it saying? What information did you gain from it?
When the predator population is higher than the normal, generally the prey population will decrease because they're getting killed and eaten.
Okay.
When the prey population is low, the predators don't have as much food, so their numbers decrease. Because there's less predators, more prey survive and reproduce, so their populations increase. When their populations increase, there's more food for predators, so their population increases, and then the cycle repeats.
Right. Everyone on board with that? Anyone wants to add in something else that they noticed from this graph? What's happening at this point? Or what's happening at this point?
The predator population reaches its peak at A, and the prey population reaches its minimum at B.
So if I were to ask, what is the population of prey that is needed to sustain, let's say about 120, or let's say how much this is, it's 130 or 140. How much population, prey population, would you at least need for them to survive? And at this point, what is the prey population right now? What happens after this point? If I were to draw a line just below it, then it tells me that the prey population is something like 40. And it tells me, this graph tells me that this is not enough for all of these predators to survive on, which is why their population starts to decrease. If it were enough, then they would have survived and it might have remained constant. But because it has decreased beyond this point, they don't have enough food. This is the point where predators don't have enough to eat. And so they start decreasing, and point B is the point, and they start to decrease. So the rate of decline of the prey population starts to decrease as well. So they're declining, but they sort of level off at this point because now there are not enough predators for them to eat. What would have happened if this curve would have hit the x-axis? If they had eaten, let's say, all of them, would the cycle have continued?
No.
What would you have seen then?
The predator population would also go to 0.
The predator population would have also just crashed down to 0, and there would have been no further population, right? So there's a delicate balance at this point. That delicate balance is reached where the predator population has also decreased. If these would have been eaten, then you would have seen a crash, and then this is when you have sort of a sort of crisis, let's say, in the ecosystem. The ecosystem is not sustainable beyond that point. But if it's sustainable, then this cycle continues, and so you see that this levels off, and then they increase up to their peak. And because they've increased, the predators now have a lot to eat, so they also start to increase and reproduce more. But at a certain time, there's way too many predators for them to increase further than that, so they start declining. It's a cycle that continues, and you can notice that this cycle sort of continues in a period of about 12 years. This cycle sort of starts off again. They start off with the same number of population, and they increase, decrease, and so on. So after another period of 12, 13 years, that cycle goes. Right? So you have an interesting behavior here, where there's a periodic behavior that you're seeing. Okay, and this is a phase portrait, what we call that. If instead of plotting the population separately with respect to time, if I were to plot the population of the predator with respect to the population of the prey, so take this as a coordinate and this as a coordinate, 100, 100, this is one of those graphs that I've plotted, then this is sort of what happens. If you go in this direction, the prey population is decreasing, so you see this, but the predator population is increasing. So when the graph is going upwards, that means predators are increasing, and when the graph is going downwards, the predators are decreasing. On the other hand, the leftwards and rightwards is for the prey. So a northeast direction sort of tells you, sorry, a north to west direction sort of tells you that predators are increasing, so this part of the graph, but prey is decreasing, right? Predators plus and predator minus, prey plus and prey minus. So prey is decreasing up until the point that they hit this point where the predator also starts decreasing to something like this. And notice what's the prey population at that point. It's something like 20 to 40. So perhaps this point has been reached. And now the predator population starts to decline as well. So you see a decline in the predator population until the prey population kicks off again and this graph moves to the right hand side. And so now you see an increase in the prey population, but still not, because it's going still horizontally. So the predator population is still not increasing yet. It increases once you reach to this point, and now it starts to take off. So it's a interesting phenomena if you see the graph being made out, but this is very nicely modeled in a set of differential equations that's over here, where X denotes the population of the prey and Y denotes the population of the predator. And so what these equations are saying, let me write them again. It's saying that the predator, the prey population with respect to time is equals to, is some function of the prey population right now multiplied by some coefficient b minus py, where b is what's the current birth rate of X, what's the current birth rate of the prey, and what's the, how much. So if there's a certain number of predators right now in the population, how much do each of them eat? That's sort of captured in this coefficient here, p. And you also have a differential equation for the predator population. And so it's Rx minus T times Y, where this is again, the predator population depends on the current prey population. The prey population depends right now on the current predator population. So it's not one differential equation. This is called a system of differential equations, where the variables are sort of depending on each other. Predator depends, this is the prey, it depends on what's the predator right now. If there's, what captures this relationship? That if there were too many predators, then there will be too few prey. What captures this relationship in this equation? What happens when I make y large in this equation?
The coefficient of X decreases.
Because of this negative sign right here. So dx by dt, that is the rate of change of X with respect to time, goes down. It could even go negative. When it goes negative, that means the prey is decreasing. So the more of y you have, the less of X you will have. On the other hand, you have an inverse relationship. The more of X you have, the more of Y you'll have. So this is actually, this has a plus sign here, because the more prey there is, the more predators can survive on that prey. So the predators start increasing. So this negative sign and this positive sign are giving that relationship, that the greater the value of X, the higher, or let me say not just Y, the rate of change of X with respect to T decreases as Y increases. And as X increases, the rate of change of Y with respect to time increases. So it's a interesting interconnected cyclical system that you have, which is modeled by this set of differential equations, which is called the Lotka-Volterra model. Okay. And so again, I'm not giving you right now the tools to solve these differential equations. Usually differential equations are difficult to solve. What I am giving you is how to look at a set of differential equations and how to interpret what they might mean and what kind of dynamics you can get out of them. So for example, if you have a simple pendulum, right? And
Sir, can
it's
you
just
pronounce the name again?
sorry.
Can you say the name again, please?
Oh, of the model. It's the Lotka-Volterra model.
Thank you.
This is not the only model for a population dynamic. You can have other models as well. And it just depends on what kind of behavior do you expect. And the idea is in this term here, this model is very important, that you think that this is a mathematical model for how you think the population evolves. It might not be completely accurate. It might capture some populations in the wild. It may not capture some other population. So you have to sort of see how accurate is your model, how much natural phenomena are you actually able to capture accurately within your mathematical model. So the more accurate your model, the more it reflects what's happening in real life, the better your model is. Okay, the more useful it is actually. And so, for example, if you have a single pendulum, it swings like this. If I were to plot its displacement, what kind of curve would I see?
Like a sine curve would be.
You would see a sine curve. In real life, would a pendulum actually behave exactly like a sine curve?
No, it would become smaller. The peaks would become smaller because of air resistance.
Because of air resistance, you actually won't see. So this is a model. This is a perfectly fine model. It's an ideal model of a pendulum which was sort of operating in a vacuum, right? Which has gravity influence on it, but it's in vacuum. If there's no air resistance, then it would go on longer and longer. But if you were to use a pendulum in real life, then you would see that the peaks would get smaller, right? And eventually the pendulum would stop. You might also see a difference between it may not be perfectly, the period might not be exactly the same as the sine wave. The period might increase or decrease. It might be a different sort of period. Okay. So, and the question is, well, what kind of differential equation can I write for that? Well, you have, so this is called simple harmonic motion. And the kind of equation that you could write to model such a behavior would involve a second derivative, because it would involve consideration of the force and the consideration of the displacement. And it would perhaps look something like this: d squared y by dx squared is some function of the displacement right now with some constant attached, maybe something like that. Or if you had some other dissipation, some other term in there, a forcing term, maybe another function of sine as well, sine y, something like that. That could be a differential equation for a pendulum, right? So highly useful, these differential equations, and they give rise to all sorts of different phenomena. You can see dissipative behavior, and what we're seeing right now are just one-dimensional examples. You could have higher dimensional examples as well. I'm going to show you a few animations that are all examples of differential equations and how useful they are. I'm not giving you right now tools to solve differential equations, because you'll have a lot of time to look at those tools and to build up your mathematical skill set to be able to solve differential equations. And you will realize that most differential equations actually can't be solved on paper. You have to employ some sort of numerical methods, some way of modeling it on the computer so that it can solve it for you. Let me share perhaps a couple of animations with you that are simple examples of say, Okay. See. Move it here. Okay, let me just run a little search because I think I misplaced it. Okay. So locate plane, locate focusing, sure. This is quite weird. I downloaded a couple of animations and I can't seem to locate them. Where's it go? Let me just locate them again. G, C, so these are ones, and where is this one? Okay, let me just show you them from my YouTube channel. Okay, here we go. Sorry for that delay. Everyone still here?
Yes.
Okay, so here's, for example, a simple, well, not so simple, this is a wave-like phenomena that I've tried to simulate and I've tried to solve it numerically. And it's again just a differential equation, in this case, a partial differential equation, which I'm solving. And what we see in this animation is sort of how we expect a certain quantity to change with respect to time. So you'll see a couple of, quantities here that it's time. dt is basically, change in time, which is a discrete steps now because I can't take infinitely small time steps. And dx is basically how much x you expect to change, right? What's the constant that you've taken. So if I were to run this, the way I'm running this, I'm trying to basically solve the differential equation. And if I solve the differential equation accurately, it's not an exact solution, it's an approximate solution. But what you see is what you would expect a wave equation to capture, right? A model of a wave equation should be able to capture a wave going, if you have a three-dimensional wave, it should go in all three directions, right? If it's on a surface, then it goes in all three directions, which is exactly what you would see if you have a droplet of water falling on the surface of a bucket. And you can see towards the end, you can start seeing some weird behavior in this box because I've sort of constrained my fluid or whatever it is inside that box. So it's sort of now interacting with this boxes, and I need to tell it what to do when it reaches those boundaries, right? So those are called boundary conditions. So I'm sort of dictating what kind of behavior it can have, right? So that's again an example of solving a differential equation. Another equation could be simply a motion of, let's say, two wave fronts. So if it wasn't a circular wave, let's assume that it's like a tide. There are two tides which are sort of split off from each other, and this one reflects from the boundary. And you can see that if it's a simple wave equation, a tide would simply just, propagate along the surface. Okay, and this is an ideal condition. I haven't taken into account the impact of damping. So eventually the tide would lose some energy if it were to reflect some physical tide, right? But since I haven't accounted for it, this just keeps on going and it reflects on the boundary and then goes back, and that one also reflects on the boundary and goes back and so on. Okay? And you could do different things with it if you wanted to add something to it. So suppose if now I were to say that there are regions of shallow water and deep water, when you have shallow and deep water, the speed of the wave changes. So in this particular simulation, what I've done is I've actually kept a region of shallow water, so the speed slows down in the middle and it's still fast in the end on the edges. So notice what happens to the wave. In the middle, it slows down, but on the sides, it's still fast. It sort of kind of focuses into this point, and you see that weird sort of behavior accumulating. And of course, once it hits, there's a multiple phenomena. Once it hits the boundary, it reflects and it comes back, and then it interacts with the original wave. And so the behavior gets very complicated, and then it becomes really hard for you to predict analytically what's going to happen, right? But eventually you can sort of see the wave sort of leveling out, and it sort of you can actually see that in the center something different is happening because of that variable speed that I've coded into this. That's wave-like phenomena that you can capture using differential equations. These are just models that I've just solved numerically. And if you want to see, let's say, see that same model from the top, it would look something like this, that these yellow parts indicate the highest part of the wave and the blue parts indicate the lowest part. So you can see that this wave is sort of coming in, and it's again, there's a slow speed in the middle, which sort of focuses in on it. And you see that interesting, and you see this reflection much more clearly when you look at it from the top, right? And you can see this region of slow behavior, and you can see all those ripples and all those interactions happening. So they're quite interesting and quite fun to play with. Here's another equation that is sort of it's a non-linear kind of equation, or you see kind of a weird behavior that initially it looked like a sine wave, but then it started increasing and it gained a sort of a layer sort of form, right? I think an example of an interior layer sort of at form between these two sides, sort of gone into phases now. A similar three-dimensional or two-dimensional example would look like this, where you start off from random noise. It's called the Allen-Kahn equation, where you start off with random noise, but eventually it separates into regions of high and low amplitude. So part of it changes, part of it goes up until, to let's say +1 and -1. So red would indicate -1 and blue would indicate +1. And what you see is actually quite an interesting example of the kind of equation that might model, the patterns on the skins of animals, right? Or the spots or those layers that get formed. They might also be following such sort of differential equations, right? Those phenomena might be quite similar to that. Okay. And here is another example of a nonlinear equation called the Kuramoto-Shevchinski equation, which sort of, you see, initially it doesn't do much, but then it starts to get really weird. It starts off something like the Burger's equation, but then it starts getting these waves and these frequencies, sort of, you start seeing more and more frequencies getting involved, and the behavior becomes quite interesting to see. And this is a nonlinear equation that was written down to sort of model the behavior of, I think, laminar flame fronts, I think. They are quite interesting behaviors, you can see. So yeah, this is just an example of what you can get. These were just examples, and I'll write down a few more examples. You have the I already mentioned the heat equation, the wave equation, the Laplace equation, the Poisson equation. These are all partial differential equations. And even in simple ODEs, you have quite interesting examples. And I also showed you this Allen-Kahn equation, and these are all very fun to play with. And you see sort of very interesting behaviors. You see chaotic behavior, you see periodic behavior. You might be able to see attraction points, and you might be able to see reflection points, right? Stable points, attraction points, and all sorts of interesting phenomena you can observe in these differential equations. Quite a rich field, and quite, again, a direct application of everything you study in calculus. So derivative, integration, basically solving a differential equation is just integration, a very complex integration. So these tools that you gain in your calculus courses will help you sort of gain an understanding of how to deal with differential equations as well. Okay. So yeah, that's my sort of, let's call it a tour, because it wasn't exactly a course. It wasn't even a crash course. It wasn't anything like that. I just gave you a few classifications. But just to give you an example of how interesting some of these things are to look at and to play with and to solve, and to how much application you have in these differential equations. Okay. All right. Any questions? Any comments?
No, sir, no questions.
All right. I hope this was very useful exercise for all of you. Hope these sessions were helpful. Hope these were insightful. Hope you learned new things. That was our intention. And yeah, if you have any feedback, if you have any comments, questions, let us know on Discord. We'll still be available. We'll be keeping that active. And we'll also update you on the participation certificates as well. Okay.
Sir, like these sessions were really amazing. Why? First of all, because like in schools and colleges, what we do is we just like take lectures and then we go do our homeworks and do classworks, and like usually it's the same, like just a repeat. Where in these sessions
Right.
there was like a good, like not a good, like an amazing level of interaction between the teacher and the students, and we not learned but also saw how we can use mathematics, how our perspective changed about mathematics. And like this was, like, just to sum up, it was an interesting, enhancing 4-week math course in the summers.
Thank you
And
for your
just
comments. Yeah.
one more thing, just to make it more interactive, I guess what could be done is like just after class, what could be done is we like you could give us some questions. Let's say if there is some good calculus you just taught us, so what could be done is like after the class you could give some good, like 4, 5, 7 questions, and then we could try on our own, so that we also get to like practice in that uh, like how we were taught in the class, so just for the application as well, so we have a good practice of that.
That makes sense. Yeah, and this was our first time running this summer school, so hopefully, and we hope to make it a regular exercise. So yeah, we'll take that into account, and perhaps next time around we'll have more, let's say, questions, and try to make it more interactive. We were sort of unsure as to why the participation levels decreased, but yeah, maybe we can. And there's lots to learn from this experience for us as well. But yeah, glad you had a better experience. And the idea was, of course, those what you learn in school and what you learn in university is, of course, an important part. But often what happens is you sort of lose the bigger picture. You sort of lose when you're, for example, when you're taking a differential equations class, you're learning lots of methods on how to solve differential equations. But you sort of lose the bigger picture into why you're doing it, what are the applications, what kind of models can you make, how do you make models, how do you check those models are accurate or not, and so on and so forth. So I think that sort of gets lost, and that's something that you have sort of motivate yourself as well, and but you have to, these sort of things, this kind of summer schools, and keeping yourself updated. Even some YouTube channels are really great at piquing your interest in certain things. So that's really important to keep, sort of to look back, step back a little bit and see why you're doing all of this stuff and why is it interesting. Because it is, at the end of the day, mathematics is really interesting, really useful, really applicative, but you sort of lose the bigger picture along the way from there. Yeah, that was our intent. Okay, anything else? Any other comments?
So I just wanted to say that before getting into the whole summer school situation, I was kind of skeptical because the topics felt a little too higher than our level. But once we got into it, it was like we were able to cope up with it and like keep up with what was being taught, not
Right.
only by Dr. Dadish, but by you as well. And again, like the other student also said, the sessions were very interactive and very different from what we do in school, like for online learning, especially like A levels I'm studying right now. So it's very different from that. And calculus being my favorite subject, I enjoyed that week a lot.
Really glad to know that.
Especially the relationship between integrals and derivatives. That was like really cool.
You should, like I mentioned on Discord, you should definitely check out the YouTube channel of Grant Sanderson and the 3 Blue 1 Brown channel. It's amazing. Grant does a much better job than I could ever hope to do as far as calculus is concerned. And those videos are just really illuminating and really interesting to look at. And I think he's also done a short series on differential equations as well. So if you thought today's class was interesting, you should check those out. Yeah, you should do that.
I'll do that.
Anyone else? Any other comments?
Yes. So I just wanted to say, well, first of all, again, thanks for the whole summer school. It really was a wonderful experience. But also in regards to like today's class and in general, I really would appreciate if you like for this week also you just say you're giving the example of 3 Blue 1 Brown. If you have any more like YouTube channels like that or books, etc., which you think आपने पढ़ी हैं, which
I have
think
lots
that
and
if
lots
you
of
could
books. I just don't want lots and lots of books to recommend. I just don't want to overwhelm. But yeah, if you think you would find it useful, if you point out resources to you, then definitely we'll point
yeah,
out
so if
some.
there's anything more that you think would be interesting, because like as of yet I have found your whole kind of I think कि आपका जो interesting आपको चीजें लगती हैं, I also happen to share kind of a similar interest. So yes,
Right.
in general, if you can recommend anything or everything plus, so I would appreciate that.
I would definitely. So there are two sorts of there are two kinds of resources when you look at mathematics sort of resources. One is the motivational kind, the intuitive kind, the conceptual kind. So for example, the stuff that Grant does, it's very conceptual, very intuitive, and the animations are wonderful. It helps you visualize the stuff really quickly and really well. So it gives you a very good intuitive understanding of what's really going on. The other material is more textbook, more rigorous, more involved in tools and techniques. And I think both of those should be looked at simultaneously. As soon as you have an intuitive understanding, you should be ready to dive into the technical details of it, because your sort of knowledge and skill set is very limited if you only get an intuitive sense. Trust me when I say this, your understanding of the material would increase 10-fold and 20-fold once you have those tools to solve those problems by yourself. When you can analyze them on paper, when you can solve them on paper. So for example, if I were to recommend something for calculus, as far as YouTube is concerned, then I can give out a few channels and I can give out some perhaps interesting books as well. But if I were to give out a reference material or a book, then I would go back to the basics, which is just something that you will see when you go into university. It's a single textbook by James Stewart, which you study in the course of 3 semesters, so Cal 1, Cal 2, Cal 3. It's one book, one heavy book, which is just the end all be all of understanding and, going through calculus and learning the techniques and studying the techniques and just learning how to solve them and learning all of these definitions and approximations and differential equations. All of that is in there. So I think I'll share some of those resources. I'll share both the kinds of materials, and I think you should be ready to sort of not only look at the motivational kind, but also to look at the rigorous kind. Be ready to, spend the summer just solving some problems and solving your questions. And I think that more than anything, that helps increase your understanding if you're able to do it yourself. It's very different when you do it in schools or in universities, because then you're doing it because you have to do it. But I think if you're really interested in something, then you should be just ready to open up a book, read something. If you find it boring, then it's very possible that the book is not great. The author hasn't made enough effort to make it interesting for you. Try to find another book. You'll eventually find a book that is easier to read, that makes you, that gives you the right understanding of the material without making you worry too much about it. But still, I would say make that part of your practice as far as mathematics is concerned. These, 12 sessions that we have were definitely there to take a step back and to look at the bigger picture and to sort of not worry about exams and assignments. Maybe, we can give a few problems so that you can have you can work on something. That's something that we'll definitely work on for the next. But here, this is a rant about everything and hopefully not about nothing. Anything else? No? Okay, hope you all had a wonderful time. We've gone over time, half an hour today as well. Sadly, I think next time when we hold these, we should have at least 4 or 5 sessions a week, not 3 sessions. I think we were a bit ambitious as far as time is concerned. Okay, have a good day. Hope you enjoyed. Let us know in Discord if you have further comments or questions. Have a good day. Bye.
Thank you, sir.
Uh,
Bye.
Bye.
Allah Hafiz.